Welcome to SERVOsoft, Size Complete Servo Systems. This tutorial shows you how to build a typical SERVOsoft project, and then review the results. Let's begin with a brief overview of the SERVOsoft interface. Here we have a new empty project. The interface is divided into 4 sections: Tree View, Graphical Layout, Component Details, and the Easy Size Wizard. The Easy Size Wizard walks you through the sizing process, starting with the system configuration, including the number of axes, bus connection, and main supply for a shared bus, name of the axis type, the motion sequence, the drive mechanism, transformation or gearbox selection, and motor and drive selection. For multi-axis systems, the above steps are repeated for each axis. Before we start, here's what the project will look like at the end of this tutorial. It will be a 3-axis gantry robot in a shared bus configuration. Starting with a new blank project, I will walk through the first axis in detail. Then I will skim over axis 2 and 3 since the steps are mostly identical to axis 1. Then I will go over the power flow configuration and look at saving energy costs. And finally, review the performance results, bill of material, and final report. First I will set 3 axes, a shared bus, and a 400 volts 3-phase mains supply. Now I will change the name of axis 1 to x-axis. You can do this from the wizard by clicking the Rename Axis button. As you can see, in the Pro version there are many mechanisms to choose from. I will select the conveyor axis type. Now I will open the sequence form and specify the motion profiles, and then right-click and open the first move, which is a dwell segment by default. First, I will change the dwell time to 1.2 seconds. Then I accept the values and close the move form by clicking OK. Now I will append a move after the first segment. When I change from a segment to a move, the input values change accordingly. Profiles can be specified based on time and distance and speed, or time and speed. I will use the motion profile values that are entered as shown here. To make things easy, first use the 1/2 or 1/3 rule and S-curving as I have done. This gets you a valid profile quickly, and then you can release the calculated Excel values and adjust them as needed. As you can see, I am using time and distance where we must move 600 millimeters in 800 milliseconds. Lastly, I have entered a 0.6 second dwell time after the move is complete. Now I could also create a separate dwell segment, but sometimes it makes sense to include the dwell time with the move. That way, when the move is copied, the dwell is included with the copied move. Next, under the Payload and Thrust tab, I can specify additional payload and thrust values specific to this move. That is, the values entered here are added to the load and thrust values specified in the mechanism form. A value can be entered for each of the move segments: acceleration, constant velocity, deceleration, and dwell. The Performance tab breaks down time and distance values for the acceleration, constant velocity, and deceleration profile segments. I accept the values and close the move form by clicking OK. Next I will duplicate and reverse step 2. Then I will open it and change the name to Move to Pick. To view only the sequence table, I can select the Data Only option. I can also just view the chart profiles by selecting the Profiles Only option, and I can switch back to the default Data and Profiles option. To save the sequence and close the sequence form, I click OK. Next I will enter the mechanism data. Here is the conveyor mechanism with its values already entered. Inertia and mass values can be entered directly or calculated using the built-in inertia and mass calculator, where dimensions and material density are specified. Under the Belt tab, there are belt parameters such as the belt mass, preload, and rigidity. And under the Load tab, I can define the load mass, which can also be entered directly or calculated using the inertia and mass calculator. I can also specify a thrust and whether it applies continuously or just during motion when velocity does not equal 0. I can also specify a counterbalance as a mass and/or force. Finally, I can include 2 different coefficients of friction. The first is between the belt and slide. used when the belt is sliding along a surface. In this case it is not, so I'll leave it at 0. The second is between the belt and load, if, for example, a box is on the conveyor and I do want the box to slip if it is accelerated too quickly. In this case, load slippage is not an issue, so I'll leave it at 0. The Limits tab is where I can add some basic safeguards. In my project, I want to prevent belt tooth shear by ensuring the drive pulley output torque does not exceed 50 Newton meters. I also want to ensure the belt tensile load, including preload, does not exceed 2000 newtons. If either of these limit values are exceeded, a message is generated in System Check. Next, I will select a gearbox by opening the gearbox database. Then I will load a list of filters I have prepared for this gearbox selection and click Apply Filters. Notice the filters that have been applied to narrow the list of possible gearboxes. I have ensured we have 10 to 300% margin on the maximum required output torque and at least 10% margin for the input speed. I have also filtered only the B&R and Stober one-stage models. Finally, I have ensured that the gearbox input shaft diameter will accept a motor shaft diameter of 24 mm, which helps narrow down the search. The current list of filters can be saved as the default filters that will be applied each time the gearbox database is open. I can do this by clicking Save as Default Filters. Or I can save them with a unique name to load them from the gearbox filters list by clicking Save As. Now I have two filter sets available as shown. Now I will choose the Stober P321 8:1 ratio gearbox by selecting the row and then clicking on OK. Next I will select the drive and motor. Notice the filters that have been applied to narrow the list of possible motors. We have ensured I have at least 10 to 500% margin on the required peak torque and speed. I have also ensured the inertia mismatch will be between 3 and 7 to 1. I will choose the 8LS A53 model as it is the lowest torque and speed motor of those listed. Next I will click on the Drive tab to select a drive. I will select the 8V1016.0 drive to see how it fits with the selected motor. Since this drive is at the top of the list, it is already selected. Note the selected drive's inverter, continuous, and peak torque curves that are shown over the motor torque curve. The 8V1016.0 is a good choice for our selected motor. Here we have a summary of the selected motor data. And similarly, a summary of the drive's inverter data. Next, let's examine the motor and inverter performance. Here I have a chart displaying the active peak and continuous rated torque curves, along with the application torque profiles in green and the RMS torque as a blue dot. I can also overlay the inverter continuous and peak current torque curves, and choose which torque profiles I'd like to see. The motor and inverter required data is shown, along with the available margin based on the motor or inverter rated values. Next, let's review the drive and motor margins, which include inputs for the bus power, inverter, and bleeder, as well as the motor. Margins allow for early warning before rated values are exceeded. This is best shown in the help file, so I will press F1. This is the help topic for the rotary motor margins. A 10% margin is shown in orange under the peak torque curve, and similarly for the RMS torque and speed margins. If the application operates outside the peak torque limit, System Check will report that the motor peak torque margin was exceeded. Next, let's examine the gearbox performance. Here we have a chart displaying the gearbox output torque versus input speed. Similar to the motor performance chart, we have the gearbox maximum and nominal output torque ratings, as well as application torque profiles and the nominal output torque, also known as the RMC torque, root mean cubed. Next, let's review the gearbox margins. Here we'll select the default values. To add the Y and Z axes, simply repeat the process that we just completed for the X axis. These axes will have slightly different masses, inertias, and sequences, but the process is the same. Now, with all three axes completed, the project looks like this. The shared bus is already enabled. but by just clicking on the Shared Bus button, you see how easy it is to change between a shared bus and a standalone application. Also, the total bus capacitance and maximum allowed bus stored energy are shown here. There are several advantages to a shared bus. The shared bus connects all drives so that the in-feed and bleeder power requirements can be shared. If and how they are shared can be configured in the Power Flow configuration form. To open the Power Flow configuration form, I can jump to that step in the wizard like this. Sometimes you can get away with one in-feed powering the bus for all axes, which is what I will do here. I will disable X and Z axes in-feed modules so that the Y-axis in-feed module alone supplies the bus power. But note that I have left all three bleeder modules enabled so that they will share the bleeder power, and the bleeder power flow is divided proportionally to each module's continuous rating. Now I will save the project and call it Gantry Robot. Now let's review the power flow through the entire project. Where rated data exists, three values are shown: the required and rated values and the margin between them. Otherwise, just the required power is shown. Now I will perform a scenario analysis by studying the effects of adding a capacitor module to the bus. The first step is to take note of the system power consumption. The system draws 325 watts of net continuous power and 8.6 kilowatts of peak power. Note that SERVOsoft tells us that if we add 0.83 millifarad or more capacitance to the bus, the bleeder energy will be reduced to zero, saving $30 a year in energy costs. Next, we add a BNR capacitor module to the bus by first opening the capacitor module database. First, I will add a vendor filter to list only BNR capacitor modules, and another filter where capacitance, C, is greater than 0.83 millifarads. Then the first capacitor module listed meets our requirements, so I will click OK. Next, let's review the system power consumption with the capacitor module added. Note that the system net continuous power has been reduced from 325 watts to 301.6 watts, and the system bleeder discharge power has been reduced by 100% to 0 watts. SERVOsoft helps engineers make intelligent decisions when designing for energy efficiency. Finally, I will open System Check and see that all components are operating within their rated data and user-specified limits. There are some warning messages in yellow, but nothing critical in red. Therefore, the design has passed System Check. Now let's review the bill of material. The bill of material contains all major components including motors, drives, in-feed, capacitor and bleeder modules, and gearboxes. The bill of material can also be copied to the clipboard or exported to a spreadsheet. I can also group the products by any column just by dragging the column header to the group drop area, for example by axis or by vendor. And I can remove the grouping by dragging the column header out of the group area. This concludes the tutorial building your first SERVOsoft project. Thank you.